I want to take a few minutes to discuss problem 16 of tutorial 3. So we have a population in the urban area that declines with time. So if you take a look at PU, which is the urban population at any time t, it is comprised of two components according to this equation. So there is a PU min, the minimum value, which is, let's say, 10,000, 100,000 as given in the question. So PU min is 100,000 and PU max is a value 75,000, and we have e to the power of minus, and Ku, right? Ku is 0.045 per year times t, and t is going to be in years, right? So this is the equation for Pu. And if you take a look at this at time 0, when you put t is equal to 0 here, what's going to happen is e to the power of 0 is going to be 1. So Pu at time 0 will be Pu max plus Pu min, right? So that will be the value of uh, the population, the urban population at time t is equal to 0. So in numbers, it is going to be equal to 175,000. Then with time, what happens is this will decay because it is e to the power of minus a positive value. So Ku is positive, t is positive, therefore Ku times t is positive, and e to the power of minus a positive number, that means e to the power of a negative number, will decay. So therefore, at time t is equal to infinity, let's say long times, right? Theoretically, t is equal to infinity, but practically long times, when t is large, then what happens is you're going to get e to the power of minus ku times t, that will go to 0. And then pu at time t is equal to infinity at long times will be equal to pu min, because the first term will drop out. So you will have 100,000 to be the final population, the urban population. So you can envisage a figure like this for the urban population. It's going to be like this. It's going to be like this. This value, the asymptotic value where it will reach at large times, this value is going to be 100,000, and starting value is going to be 175,000. Okay, so this is a model that kind of is a decaying function. Now, when you come to the suburban population, which is seen to grow, and it is given by this expression, this is called the logistic equation. This is like the S-shaped growth that you will see in many phenomena. For example, if you're working on biochemical reactions, this kind of a S-shaped phenomena is very common in the growth of, let's say, a microbial community. It is also the same with the growth of cities, right? So usually if you look at how the city grows with time, initially it will start from somewhere, the growth will be slow, but then over time things will pick up, and then it will become quite fast, and then with this upper limit on resources available, it will flatten out. So this is what is called the logistic growth or the S-shaped growth. Okay, it may not be as pronounced as this, it can be something, but you will have this kind of a S shape, right? If you want to draw it like that, something like this. This is what is the S-shaped growth. If you dive into it, what happens is PS max is given to be 300,000. So PS max is 300,000. So this is given to be 300,000. P naught is given to be 10,000 people, 10,000. And KS, right, is 0.08. KS is 0.08, T is time. So this is how the population in suburban areas changes with time. Now, if you put t is equal to 0, that means at the starting time, what is the suburban population? PS 0, time t is equal to 0. What happens to e to the power of minus kst? So this will be 1. So we are going to have 1 plus PS max by P naught minus 1. So this 1 and this 1 will cancel. When t is equal to 0, this basically is 1. So that's not there. So this plus 1 cancels with this minus 1, leaving you with PS max by P naught in the denominator. In the numerator, you have PS max. So what happens is PS 0 will be equal to P naught. So if you put t is equal to 0 in this expression, you're going to get P naught. So P naught basically is the starting value of the population. And what happens is, let's look at the other extreme, which is large times. That means that t is equal to infinity. When t is equal to infinity, what happens is this one will become 0. So this multiplied by this will become 0 at t is equal to infinity. And the denominator will just be 1. So PS at large times at t is equal to infinity will reach PS max. So PS at t is equal to infinity or tending to infinity will reach PS max. So this is the limits to growth, if you like. If you plot this, right, if you substitute intermediate values, you will see you will get a S-shaped pattern, as we shall see with the MATLAB code later. So if you start with P0, which is 10,000 people, so you are starting somewhere down here. Let me use a different ink. Um, so if you start somewhere here at 10,000, so you will see slowly this will pick up and it will reach 300,000 ultimately. So this ultimately will reach 300,000. So these graphs are not drawn to scale, just cartoon illustrations. So there will be a point at which the two populations will be the same. And there will be a point where the suburban population, suburban which is in green, that will be 20% more than the urban population. So we can in fact plot the ratio of P suburban by P urban. So once you have the data for urban population for year 1, year 2, year 3, year 4, year 5 till let's say year 150, and you have the same thing for the suburban population, so we can divide the corresponding entries and we can draw this ratio as a function of time. So at time t is equal to 0, PSU as we have noted is P naught, which is 10,000. At time t is equal to 0, PU is 175,000. All right. So if you take the ratio, it will be 10,000 by 175,000 at the start. So it starts at, let's say, a value like 0.06 or something. 10,000 divided by 175,000 will be 0.06 roughly. Then at the end time, what you see is the suburban population will be 300,000, which is PS max, and the urban population will be 100,000. So this ratio will start from 0.06 and it will change and then it will reach a value of 3. Somewhere this ratio is going to be 1.2. That is where the suburban population is 20% more than the urban population. That is what is asked in the question. So determine the time and corresponding values of PUT and PST when the suburban population is 20% larger than the city. So first of all, we need to locate the time at which the ratio is going to be 1.2. Once we get that time, then we can plug the times in this expression and this expression to get the populations, right? So that will be the approach. So we are going to adopt a graphical approach to this problem. That means we will generate PU of t and PS of t and then calculate the ratio and plot it versus time. And then we will zoom in on that plot to find out the time at which the ratio is 1.2. So let us see how we'll implement it in MATLAB. So I'm taking t to start at time 0 and to go till 120 years. All right, because I know from other ideas that I have learned that the population will take about 120 years to reach steady state. Okay, that comes from my understanding of system dynamics, right? So if you do a course on process control, you will learn that a first order system will reach steady state in 5 time constants. So the time constant is denoted by the symbol tau. So a system to reach steady state will take 5 time constants. And in this case, the time constant is going to be 5. The time constant will be 1 by Ku. Ku is the decay rate, if you like. So it is going to be 5 divided by 0.045. So this is approximately 120. Though not exactly 120, it is approximately 120. So I know it would make sense for me to try to plot the populations for 120 years. Of course, if you did not have a knowledge of system dynamics, which for a junior level student at your level is not something fair to expect. So you have to try with different t values, the n t values, and see what time is it taking for the population to stabilize. So try with 10 and plot it and see whether the population has reached a steady state value. If it is still going up or if it is still coming down, it has not flattened out, then you increase from 10 to let's say 40. Again, repeat the process until the two curves for PS and PU flatten out. So that is some way in which you can arrive at this higher number. Okay, so time is 0 in steps of 0.01 years till 120. Then I input the values given in the question for KU, KS, PU max, PU min, right? So PS max and P0. So 1E4 means 1 into 10 to the power of 4, which is 10,000. 3E5 means 3 into 10 to the power of 5, which means 300,000, and so on. All right. And then just an equation for the urban population. So whatever is the formula given, PU, urban population, is equal to PU max times exponential of minus KU times T, and then add PU min to that. So this is something that is easy. The suburban population formula is a little complicated. All right. So what I do is I first program the denominator of PS, right? So I just program this part, the denominator of it. So it is going to be equal to 1 plus PS max by P naught minus 1. So this is in brackets. So you have to use the brackets carefully. So this bracket finishes this fellow. This bracket is for PS max by P naught. I'm a little careful with brackets, right? So I don't hesitate to use more brackets just to get the formula right. So times exponential of KST, very much like what we had for PU. So multiplied by exponential of KS times T negative. And so what happens is this PS max by P naught is constant. So PS max by P naught minus 1 is also a constant. It's like a number. So I'm multiplying that number with e to the power of minus KST. And to the whole thing, right? So this is the whole thing. I add 1, which is this one. So program the formula correctly. Now, if you know, then PS will be a vector, right? Then PS now will be a vector, because for every time t is equal to 0, t is equal to 0.01, t is equal to 0.02, etc., it will have found out the value of the denominator. So now when I have to calculate PS, which is going to be PS max by the denominator, I have to use element by element operation. That means PS max is a number, right? PS max is 300,000. So 300,000 divided by something, the denominator, that changes with time. So this denominator is a vector. So every element of that vector I take and I do 300,000 by that value. So it is going to be an element by element operation. So I'll take the first element of den PS and then I will do 300,000 by that first element. So I'll get the first element of PS. Then I take the second element of den PS and I will do 300,000 by the second element of den PS. That will give me a number and that will be the second element of PS and so on. So this is how I generate PS. Once I generate PS and PU, I'm going to plot these two populations, right? I'm going to plot PU with black color and I'm going to plot PS versus time. So time is on the horizontal axis, PU is on the vertical axis here, and then I hold on. So in the same plot that I plot PU versus time, I also plot PS versus time, the suburban population versus time, but the suburban population in blue color with dash dot. And then I label the X and Y axis appropriately using X label and Y label, and then I add a legend, right? That means I will tell it which curve is which population. So since I've done PU first, so the first legend will be urban. I've plotted PS second in that same graph, so the second legend will be suburban. So when I execute these lines of code, or when MATLAB executes these lines of code, you will see this graph being produced. So you can see the labels, you can see the legends, and you can see the suburban population and the urban population. The urban population is in black, the suburban population is in blue, dash dot line, the urban population is black continuous line. Next, what I do is I want to plot the population ratio as I explained earlier. So I'm going to take every element of suburban population and divide it by the corresponding element of PU population. So population ratio at any time is the PS value divided by the corresponding PU value. That's the ratio, the suburban population to urban population at each point in time that I've computed those two populations. So I've used the same T for both. It's clear and easy. So then what I do is once I've calculated pop ratio, I'm plotting population ratio versus time in red color. And of course, I'm using X label, Y label appropriately, and I'm using grid on to just be able to see what's going on. So when I do that, I get this plot. All right. So please note the S-shaped curve of the suburban population. So that's the logistic growth. And then this being the ratio of SU by U or S by U, right? Suburban population to urban population, what happens is it has this particular shape. It starts at somewhere like 0.0571, which is 10,000 by 175,000. And it goes all the way as we thought it will go till 3. And 120 years seems just nice to stabilize, right? So this curve has flattened out. This curve has also flattened out. So the ratio has more or less flattened out. So 120 is not a bad choice. So if you look at where this population ratio is 1.2, so you can using the zoom feature in the MATLAB figure plot, and you get an answer close to 40 years, right? And if you zoom in really, and to my eyes, it seemed like 39.7 years. So that is the time at which the suburban population will be 20% in excess of the urban population, given the parameters and the equations, etc. Now I can take this 39.7, t is equal to 39.7, and I can plug it into these two expressions. All the other things are known, just plug in the value of t is equal to 39.7 and you can get the value of urban and suburban populations. Or you can come to this graph and you can zoom in at t is equal to 39.7, somewhere there. And then you can read off the value from the black curve and the value from the blue curve. And then you can report those answers. Okay, that's about it. Thank you for your time.